Greetings, my name is Guillem Arias and Maria Vanrell is my supervisor. In this presentation, Understanding Trained Convolutional Networks by Indexing Neuron Selectivity and Network Connectivity, you will see the aim of my investigations and what we have achieved so far. The main goal of this thesis is to understand better what happens inside neural networks, which are often seen as black box models. In order to do so, we divide our work in two categories: understanding individual neurons and understanding the connections between those individual neurons. The first step to understand better individual neurons is going to be to visualize them. There are many methods to visualize neurons inside a network, such as trying to generate an image that maximally activates a neuron, and try to visualize the filters directly, or trying to see the activations over the images. However, in this work we will be using the neuron feature. The neuron feature is the weighted average of the top scoring images of the neuron. As they can be seen here, these are the top scoring images, which are the parts of the image that maximally trigger that neuron, and here we can see the combination of those top scoring images, which is what we call the neuron feature. We decided to use the neuron feature because it gives a more or less realistic image of what is triggering the neuron, and we can use the information of the top scoring images to calculate further indexes. Now that we can visualize individual neurons, we want to have a quantitative measurement of what is triggering them. To do so, we define the selectivity index, which is calculated using the weighted average of the percentage of pixels belonging to a certain concept in the top scoring images. This gives us a quantitative measure of the stimulus that are triggering that neuron. For example, in this neuron feature that we can see right here, we can see that the most present color is the color pink because of the skin. The class that it's more present is sunglasses or sunglass, and it's detecting basically a person. And this person has these different parts. Once we are able to visualize individual neurons, we want to understand the network as a whole. For this reason, we want to quantify the connection between neurons. To do so, we define the relevance index, which measures the strength of the connection between one neuron and another one of a shallower layer. It is calculated by averaging the drop in activation of the top scoring images of a neuron after removing a neuron of a shallower layer. As you can see here, we have the activations of the top scoring images of a neuron, and after removing a neuron of a shallower layer, we have the same activations which are lower. So basically, the area between these two lines would give us the value of the relevance index. One of the benefits of using the relevance index is that it's a very flexible method. It can be used to calculate the strength of the connection between any neurons of different layers. They don't have to be consecutive layers. And it also can be used in any architecture. It works in non-convolutional layers also. In lower layers, we have been able to find two types of connections: relevant and irrelevant. Relevant neurons cause a drop in activation when they are removed, while the irrelevant don't. However, the most interesting finding was a third class that appeared in higher levels, which we call the inhibitory connection. Removing a neuron with an inhibitory connection would cause a higher activation on the upper neuron. This is a common type of connection present in neurons of living beings, and could be the key to understand the appearance of complex concepts in the network. Finally, a relevance index is helping us to understand how the concepts are created in the network. Here we can see an example of a neuron which is able to detect cyan and magenta, and this neuron is created by the combination of the neurons in a lower layer which can only detect the color pink, red, or cyan. In a near future, we will be investigating more about the relevant neurons and the inhibitory neurons and the combination of both, and how this combination can help to create more complex concepts inside the network. Ideally, with this information, we would be able to isolate subnetworks inside neural networks in charge of specific class or tasks. This will help us to fulfill our objective to visualize the connections, and with this we will be able to visualize the whole network. Here is an example of a subnetwork that we were able to identify. We can see that the concept eye is created first and the concept body, and both of them are combined to create the concept person or face. Our goal would be to extend a visualization like this to the whole network. This would allow us to understand better networks and the criteria that it has to take some decisions. I hope that you found this topic interesting, and thank you for your attention.